With the hypothesis testing, we said we basically have two different kinds of hypotheses. We said we have the null hypothesis, where we usually start off with saying, actually, when we compare two samples, the sample means only differ by the fact that there is sampling errors. Otherwise, there is no difference between the sample means. So no difference between sample means other than caused by sampling error. That's our H null hypothesis. And very often this is abbreviated as x1 equals x2. X bar mean of one sample is the same as mean of the second sample. And we said, well, that's fine, but very often we are more interested in the alternative hypothesis. And the alternative hypothesis says, in its most basic form, that, bless you, sample means are different and this is caused by sampling error. We will never be able to avoid the sampling error. This is caused by sampling error and additional effects. Yeah, that's the alternative hypothesis. So mathematically, we could write this as x1 unequal x2. And this leaves us with two options. It leaves us with the option that x1 is bigger than x2, or x1 is smaller than x2. So I've got two options here, and that is, when I phrase it like that, this would refer to a two-tailed test, because I've got two options. Alternative to these two-tailed options, I can say, in my alternative hypothesis, one sample, so here, for example, x1, the mean, is bigger, bless you, than x2. And this is caused by sampling error and an additional effect. So I would write this as x1 is bigger than x2. So I have only one option here when I say it like that. And this would give me a one-tailed test. And I've put up a video on my YouTube channel. You've all seen my YouTube channel, I guess. So if you want to subscribe, PK11 Kent. Just in case, yeah. My son thought he is going to do me a favor, and he said, I'm going to subscribe to your channel, Daddy. So he is my 1000th subscriber, and I was very proud of him. Not that he knows anything about that stuff, but he said, well, to make you happy, Daddy. Thank you, yes. Thank you. So when to use a two-tailed or when to use a one-tailed test? Usually, unless otherwise instructed, I would always go for a two-tailed test, because it leaves your options open. Yeah? I told you also that the way we measure whether there is a difference or not is very commonly done with the p-value. And this p-value is usually set in context with the alpha, the significance level. Alpha is also commonly referred to as how much of an error do we want to make. It's also correlated with what is called a type 1 error. And I don't want to go too much into detail, but a type 1 error is defined as assuming that there is an effect when there is no effect. Just to give you an example. Oh yeah, can I play with you for a moment? A type 1 error, can you stand up for a moment, please? A type 1 error would be to say there is an effect where there is no effect. Can you turn? Sorry. You're pregnant. Okay. Right? So he can't be pregnant, obviously. Biology, thank you. You can sit down. Biology is against that, yeah? But the error that I make is I say something where there is no effect. That's a type 1 error. Type 2 error would be I say there is no effect where there is one. When I go to a pregnant lady and say, oh, you're not pregnant, that's a type 2 error. But let's not worry about that too much. Very often we say we accept that in, let's say, 5% of cases we make a type 1 error. So here, usually, or very common, this alpha is set to 5%. In 5% of the cases, we accept that we make a type 1 error. And I told you, we accept a null hypothesis if the p-value is larger than the alpha. And we reject the null hypothesis if the p-value is smaller than alpha. Okay? And the mnemonic that I told you is if p is low, h naught must go. If p is high, h naught can stay. And you have to say that in an Australian accent, not a German accent. Sounds stupid, right? So, and that holds basically true for all hypothesis testing that you will do. That's all to it. I'm not going to show you how the equation works for this hypothesis testing, for the different tests, because nobody in their right mind is going to do that by hand. And obviously, I'm not going to expect that from you in an exam or in a test or something like that. But I will show you later on how you can do that in Excel or in Google Sheets. Has anyone done hypothesis testing in Excel? You? 1, 2? Not many people. But there's a little, there's a little trick to that.
Where you just calculate it by hand?
No. Where you can actually use an Excel function to do hypothesis testing. you are probably now starting to fume inwardly because your bloody teachers at A-levels, they made you calculate that by hand, didn't they?
Yeah.
Some say yes, others say no. Some did. I mean, how on earth would you want to do that? Calculating it by hand. Can you remember it, how it's done? You can.
Yeah. Because I did for normal distribution, did for binomial, did for every distribution. It's easy.
Smack my bottom and call me Susie. Wow. Okay. What are you going? What are you doing here? Woohoo. Well, anyway, I show you how it's done with a spreadsheet function. But before you do that, I want to introduce you to two different kinds of tests. Well, there are several tests. And first of all, I want to introduce you to a test where we compare the means of two samples, which we have sort of implied when we talked about the null hypothesis. So comparing two means of samples. And the first question, when we have two samples, so we have a sample A and a sample B with data points here, we need to identify whether these samples are paired or not paired. Paired or not paired. Because this has a major impact on the kind of test that we are going to do. Paired means basically we look at one sample, at one datum before something happened to it and after it happened to it. So we are looking at the same sort of person or the same thing before something happened and after it happened. So, for example, you can compare the length of my compare the length of my hair before I went to the hairdresser and after when I went to the hairdresser. Yeah? So it's paired. It's still me. It's me. After I went to the hairdresser, although, you know, sometimes people say, did you have an accident with a lawnmower? It's still me. Yeah? So this is paired. Paired means before and after. It's also referred to as a dependent test. And if you look at it, when you count the number of data points, you would always expect that the number of data points before is the same as the number of data points afterwards, unless the hairdresser kills somebody. Right? Chops off an ear or something like that. And but that luckily doesn't happen so often, so we can ignore that. So the number of data, the counts of data for before and after must be the same. So that's paired or dependent. What's not dependent? What is unpaired? And independent? Well, it is just simply I take some measurements here. For example, I calculate the colonies on a plate with antibiotic, and then I do the same experiment, and I calculate the colonies on plates without the antibiotic. It doesn't have to be the same number of plates. It can be different counts. And it's different plates. The plates don't know anything about each other. It's not a before and after. It is just simply, these are samples here, and here we've got samples there. This is all that we need to discriminate between paired and unpaired test. Paired before and after, unpaired, just simply some samples. Okay, does it make sense? Fantastic. So, what we can basically do is we can look at a t-test. Do you know where this t-test comes from? Why it's called t-test? No? No, it doesn't have anything to do with tea, although people from the Tea Society try to convince me. Is there a member here of the Tea Society? Hands up. Oh, fantastic. No, that's great. I mean, I never understood what you guys are doing. What are you doing, William? You drink tea? Drink tea? You just sit there and drink tea. Sorry? Cake. Can I become a member? Woohoo! So what you're saying is basically you're doing a tea test. You test the tea. Ah, is it paired or unpaired? Oh, you don't know. Okay, good. Now, actually, the t-test came from another brew in the early 1910s or so. The Guinness Brewery in Dublin introduced a quality assurance system because they wanted to make sure that each batch of Guinness has the same quality. So they employed a young, I think, statistician or so to come up with an idea how you can compare different samples. And he came up with this fantastic test. But the Guinness Brewery did not allow him to publish his test. So he published it under a pseudonym, which was Student T. Right? And that is how the t-test came up. Can't remember what his name was. Didn't start with a T, but only then the Guinness Brewery allowed him to publish it if it was under a pseudonym, and nobody could find out that it was related to Guinness, because that was sort of their trademark secret. So now you know where it comes from. By the way, I'm not going to ask it in a test, just in case you wonder. Okay, so we have a t-test. We can distinguish between a paired and a non-paired test, or dependent and independent test. And very often you will find that there are different sort of tricks and equations depending on whether the variance of both samples is the same. Both samples is equal or not. Usually my reaction is always assume that the variances are different. You make a slight mistake if they are the same, but it's not as big as the other way around. Right. So far, so good? Yeah? Now I want to show you something. I want to show you something that is, what I mean by that is an introduction of a different concept. It's called the effect size. So here in our example, we saw that P equals 0.017. And we would say there is a very clear effect, a statistical effect. It is significant from a statistic point of view. But is it really something that we need to bother, that we need to worry about? If the effect is really small, then who gives a damn? If the effect is massive, then of course I need to do something. I can't disadvantage the morning people compared to the afternoon people. And in order to calculate this effect size, there are some very clever ways of dealing with that. I just want to briefly mention to you what is called the Cohens D factor, which basically is more or less calculated as, you will see that as D equals the differences between the means divided by the standard deviation. And usually it is, when you look it up in Wikipedia, you will find it that this standard deviation have a little index, which means pooled standard deviations. There's an equation for that, but I don't want to bother you with that. So when you do this, generally accepted is that if D is between 0 and, let's say, 0.2, this effect is considered as marginal, or not really. You really need to look very, very hard to find that there is an effect. There is a statistical effect. Statistically, it's significant, but it's really minute. You can't really, unless you drill into the data, who cares? From 0.2 to about 0.5, there is a medium size effect. That means, yes, there is an effect, and yes, you will notice it. And anything above 0.5 is considered, or 0.5 to 0.8, let's do it this way. There is, and they call it quite noticeable, and anything above 0.8 is large. So even somebody who has no idea about statistics will see, wow, there is an effect. So when you usually do something in, when you work for a pharma company or something like that, they always go for a D larger than 0.8 because they want to develop drugs that really do it. Yeah? Now, in this particular case, in case of the difference between the afternoon and the morning group, the D factor was 0.33. So this tells us, this Cohen D factor tells us, yes, there is an effect. It's not huge, but there is an effect there. Are you tattooing her? Okay, fine. So there is an effect there, right? It is statistically significant, the difference, and there's an effect. What would you do if, for example, p equals 0.3, alpha equals 0.05? What's the D? First of all, P lower or higher? It's higher. What does high mean? We accept the null hypothesis, so there's no statistically significant case here to make, so D is completely meaningless. Yeah? You can do the Cohens D only if P is lower than alpha. Only if there is a statistical effect then. Because the question is it small, medium, or large, this effect? If there's no statistical significance there, why bother? You don't do a D. Yeah? Now, in our case, I really, really, really want to know why the morning group performs worse than the afternoon group. If it is of any consolation to you guys, this is a well-known phenomenon in the School of Biosciences. It's tradition. Over many, many years, the morning groups perform worse than the afternoon groups. And we don't have a freaking clue why this is. But I guarantee you will find out one day. Right? So, what I showed you today was the different t-tests, how you can apply these t-tests to your spreadsheet program, and I will give you some exercises to do that, to get familiar with that. And I also introduced you to the Cohens D, but I will not ask Cohens D in an exam. Okay? Happy with that? Go in peace. Good luck for tomorrow. And can I have the sign-in sheets back?